All right, let's continue with section 1.5. Let's look at continuity of compositions. Where is the function continuous? H of x is equal to the sine of x squared. Now look at this as an inside part and an outside part. Outside function is your sine of something. Inside function is x squared. So whenever you have an outside and an inside like this, and you're looking for continuity, you want to look at the inside first. Where is the inside? Where is x squared continuous? Well, that's a polynomial, so that's continuous everywhere. Now, whenever I say continuous everywhere, I mean on all real numbers, okay? So we're going to say all real numbers, okay? We're not talking about the imaginaries and so forth. All right, so we looked at the inside already. Let's look at the outside function now. Where's the sine function continuous? Sine function is going to meet those three conditions of continuity everywhere at all real numbers, okay? So the sine function, or the sine of x, I could say, is continuous at all real numbers. So if the inside function is continuous at all real numbers, the outside function is continuous at all real numbers, I could say h of x is continuous at all real numbers. Right, notice we had an outside, we had an inside function that we had to deal with. All right, so I'm going to erase this stuff, and I want to look at part B. I'm just going to need more room so I don't crunch everything up, kind of like I did on that last video there. Let's see, part B, same directions. Let me go ahead and get rid of all this so I have plenty of room here to work with. So same directions, find where the function is continuous, and let's see, this time we're going to have part B, and part B is going to be f of x is equal to the natural log of 1 plus cosine of x. All right, so let's find out where this function is continuous. Now, if we look at this as an outside function and an inside function, here's my inside function, right? So where is the cosine function plus 1 continuous? Well, what is the cosine function plus 1? That's just the cosine function, which we learned from trig. Looks like that, right? Shift it, though, 1 unit up. So take this baby and shift everything 1 unit up and so forth, okay? So actually, that's going to be continuous everywhere. There are no breaks, skips, or jumps in the graph, and it actually meets the three conditions of continuity. So I could say that 1 plus cosine of x is continuous at all real numbers. That takes care of the inside. What about the outside function, the natural log? So let's look at this for the natural log of x. Now, what do we know about the natural log function? The argument of it, like whenever I have the natural log of x, this argument right here has to be positive, has to be greater than, not 1, greater than 0. It has to be greater than 0. So what I got to make sure here is that my argument is greater than 0. Now, what was my argument here? 1 plus cosine of x. I need to make sure all that is greater than 0. Now, let's go ahead and solve this. So if I go ahead and solve this, I get cosine of x is greater than -1 if I subtract 1 from both sides. And I want to find all values of x here where the cosine of that is greater than -1. Let's think about this for a second. Where the cosine of x is greater than 1. which are the cosine function over here. That was -1, that was 1. That's y is equal to the cosine of x. Now, where is that thing greater than -1? Well, right here is equal to -1. Right here is equal to -1. But all the rest of the graph, like all this stuff and this stuff, is greater than -1. It's above -1, right? All this stuff is above -1, and so forth. So where is it greater than -1? Well, that's where it's not equal to -1 right here. So really, what this boils down to is, let's find out where the cosine of x is not equal to -1. Okay? Well, let's solve this. Where is the cosine of x equal to then -1? Think about that. Think about your unit circle. You do not have the unit circle memorized. Definitely memorize it for this course. You're going to see it over and over again in this course, Calc 1, and so forth. Okay? On my unit circle, what do I have? I have 1, 0. I have 0, 1. I have -1, 0. I have 0, -1. Now remember how these order pairs run. These order pairs run the cosine of theta, sine of theta, right? So in other words, the first number here is the cosine value. The second number here in the order pair is the sine value of the angle. So let's go back to this part here, cosine of x, and let's look at where it's equal to -1. Where's my cosine? Where's the first number in this order pair equal to -1? Right here, right? Well, right there, what is this angle right here? What is that angle right there? Wouldn't that be pi? So I'm going to say x is equal to pi. And technically now I need to put not equal to here and here. So I'm going to go ahead and do that. Where else do we have a cosine that is -1? Where else do we have that? Well, also have it whenever I go like that, right? So what is that then? That's another 2 pi from where we were at here, pi. So what's pi plus 2 pi? 3 pi. What if I go around 2 pi more? Then I'll get 5 pi. What if I go around 2 pi more? I get 7 pi. And you can see the pattern keeps going here. Now, I just considered going around in the positive direction. What if I were to consider going around in the negative direction, like a negative pi? I'll go around negative pi. Isn't my cosine -1 again? Sure is. So I need to consider plus or minus pi. Same thing here. I need to consider plus or minus 3 pi, plus or minus 5 pi, plus or minus 7 pi. Okay, so what is it asking for? It's asking for, if we go back and look at the original directions we had written on the board earlier, where is this function continuous? The inside was continuous at all real numbers, but the outside, I got to be careful. So the outside is continuous at all real numbers except these right here. So I can say f of x is continuous at all real numbers, such that, now there are different ways to write this. I'm going to write such that x is not equal to plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, plus or minus 7 pi. Make sure you put that dot, dot, dot. That's very important because you're showing that it keeps on going. It's not just pi through 7 pi. Now, you could have wrote this as what, 2n plus 1 pi, where n is integer, okay? That would have been perfectly fine. All right, but you don't have to do it that way. All right, so let's see. One more thing I want to look at here, okay? Let me go ahead and erase this board. I don't see a way to scroll down to the next page with this, which I really don't like, but gotta live with it, right? All right, so let's look at, we have a theorem, and it reads something like, give me a second here, I'm gonna write it down as I read it. Let me erase all this mess real quick. I don't know why, but I feel like I gotta be talking whenever I'm doing something like erasing. All right. Look at the theorem that says, if the limit as x approaches c, limit as x approaches c, g of x is equal to L, g of x is equal to L, and if the function f is continuous at L1, I'm sorry, at L, and if the function f is continuous at L, then the limit as x approaches c, of f of g of x is equal to f of L. That is the limit as x approaches c, of f of g of x is equal to f evaluated at the limit as x approaches c of g of x. All right, well, how does that help us? Well, I'm glad you asked. Find the limit as x approaches 3 of the absolute value of 15 minus x squared. I have no idea where my phone is going off here. Turn that off for you. All right, so what does this part right here mean, okay? That means that if I have a function f that is continuous at the limit of g, then I could take this limit right here and I could bring it to the inside there, okay? Evaluate that limit of g, and then evaluate f at that limit, as long as that limit exists and f is what? Continuous there. So basically, here's what this is. This says on this problem, I have what? I have the absolute value function as my outside function, and I have 15 minus x squared as my inside function. So what I try to do is I try to say, okay, let's bring this limit to the inside of my absolute value sides and try to see if that limit exists, first of all. Well, let's look at that limit there, okay? What do we know about that limit of 15 minus x squared? We know that's the limit of a polynomial. So what do I know about that? I know that I could just sub in 3 for x here. So I have the absolute value of 15 minus 3 squared. All right, so that's 15 minus 9 in those absolute values. What's 15 minus 9? 6, you say? It's the absolute value of 6. 6. Notice I could do that because this limit did exist here, and my absolute value function, my outside function was continuous at that 6. Because the absolute value function is continuous on all real numbers. All right, final example for this section. Let me see if this works right here. No, it definitely does not. I thought I could clear everything off of there all at once. And no can do. All right, so the next example is going to say, suppose f and g are continuous functions. Suppose f and g are continuous functions. Let me get all this over here. Suppose f and g. Suppose f and g are continuous functions. Continuous functions. Such that f of 3 is equal to 5, and the limit as x approaches 3 of f of x plus 9 times g of x is equal to 68. Then it says find g of 3, find g evaluated at 3, and the limit as x approaches 3 of g of x. All right, so I've got a little bit of work to do right here. Suppose f and g are continuous functions such that, okay, let's first of all deal with this part right here, okay? Now, we said earlier, we have not used this yet, but we said earlier that if f and g are continuous functions, then f plus g is continuous. We're going to use that fact, okay? We're going to use also the fact that we can go ahead and take this limit and bring it into the inside, take this limit and bring it into the inside there, okay? That was just a properties of limits from one of the earlier sections. All right, so I'm going to start out with this limit. As x approaches 3, f of x plus 9 times g of x equal to 68. All right, I can do a rewrite. I can say this is the limit as x approaches 3 of f of x plus the limit as x approaches 3 of 9 times g of x is equal to 68. What else did we say in that earlier section? We said if we have a constant times a function like this that we're taking the limit of, we can pull this constant to the front here. So I can do a rewrite limit as x approaches 3 f of x plus 9 times the limit as x approaches 3 g of x is equal to 68. I guess technically I'm not even using this right here. But let me use the fact that f and g are continuous functions. They tell me that f and g are continuous functions. So what does that mean? Okay, let's see what that means. At x is equal to 3, if I have continuous functions, doesn't that mean for f, condition 1, f of 3 is defined? Condition 2, the limit as x approaches 3 f of x exists, condition 2. And condition 3, doesn't it mean that the limit as x approaches 3 of f of x is equal to f of 3? Sure does. Look at condition number 3 right here. If f is continuous, then that condition holds. How about right here? F is continuous, so what is his limit as x approaches 3 of f of x? Same thing as what? F of 3. So I could call this whole limit f of 3. Plus 9 times, I could do the same thing with this limit here. I could say this is the same thing as g of 3 since my function g is continuous at 3. It's equal to 68. Well, what did they tell us up in the problem? Told us up in the problem that f of 3 is 5. So for f of 3 here, I'm going to sub in 5. So I'm going to have 5 plus 9 times g of 3 is equal to 68. Well, just solve for g of 3. So it's 9 times g of 3 is equal to 63. So g of 3 is equal to 7. That's part of what they wanted me to find, right? Find g of 3. What else do they want me to find? They want me to find this stuff, right? Limit as x approaches 3 of g of x. Well, if it's continuous at 3, wouldn't that limit as x approaches 3 of g of x equal to the same thing as this? Sure would be. There we go.